Sí, eso espero. Una lección no sé exactamente
Whatever drawings.
Ya está bien.
Oh my god.
I'm going to the next page anyway. So. But these do get saved in,
Yeah,
in the iPad.
it's saved right
So
there.
you want to move them.
We're online. Everybody's
Okay.
hearing.
All right. And let's
Yeah.
try sitting down this time. Feels kind of fun.
Okay.
Okay. Welcome back.
I just need to check the other thing.
Sure, take your time.
A little bit. This is recording. Yeah, this is recording.
Okay, so we have we've seen some interesting things in topology. We've seen various topological spaces. Well, the most interesting ones we've seen are the set of real numbers, and then the set of points in the plane, R2. So in fact, what we're going to do is we're going to generalize those topological spaces into, into the same family of topological spaces. So let me bombard you with definitions for a little while. What's a vector space? Vector space over real numbers. So this is going to be basically generalizing the properties of the real numbers that I gave you earlier. The vector space over R is a set V. Elements of V are called vectors with two operations. In this context, operation is a fancy word for a function. So I have a map that takes ordered pairs. Well, yeah, it takes ordered pairs or pairs. Let's say so. Alpha here is a real number. V is an element of V. In fact, let me clarify this a little bit. So I have a map like this. I don't give my map a name, I just give it this notation. So the pair alpha V, where alpha is a real number, and V is a element of V called a vector, gets mapped to something we just call alpha V. It's like some kind of multiplication. So this is what we call scalar multiplication. We also have an operation like this, where I take a pair of vectors and I produce V, what's called V plus W. This is called vector addition. Okay, so what properties should these two things behave? So such that, so some of these properties we've seen for the real numbers. Let me write them down kind of sloppily so we don't spend too much time on this. Here I have U plus V plus W. So the parentheses mean order of operations is the same as U plus V plus W. V plus W is the same as W plus V. We have something that plays the role of 0. So I draw it as 0, but I put an arrow over it to remind. So not, oops, not to be confused with the real number 0. We have a notion of minus an element of V. So if I do V plus minus V, I get 0, which is call it the 0 vector. What else? How about scalar multiplication? We haven't used scalar multiplication yet. So here I have alpha times V plus W is alpha V plus alpha W. And then here I have a sum of two scalars, alpha plus beta, let's say, times V is equal to alpha V plus beta V. And there's one more thing. It doesn't follow from the other properties of a vector space, so don't try and prove it. But if you multiply a vector by 1, nothing happens. 1 times V is equal to V. Okay. So there's a vector space, will be common object of study in linear algebra. I'll tell you what a normed vector space is. A normed vector space, again over R, is a pair, V. And let me tell you what this is. So V is a vector space over R. And this other thing here, I have a pair of vertical lines. This is a map from V to R. So the map just works like this. If I have a vector V, I can produce the real number where I put those vertical lines around V. So that's So this gadget, this function, is called the norm. So this is the norm of the vector V. Oh, there's some properties of the norm. The norm of a vector, so it's a real number. It cannot be negative. It's always greater than or equal to 0. And in fact, it's equal to 0 if and only if that vector is the 0 vector. Finally, almost finally, so the norm of a scalar times a vector is always the absolute value of the scalar, that real number, times the norm of the vector. And then finally, so what happens with addition? Well, the norm of a sum does not have to be the sum of the norms. That's too restrictive. It has to be less than or equal to sum of the norms. Okay, so to continue with the bombardment of definitions, actually these definitions are in increasing order of generality, as we'll explain in a minute. A metric space is a pair, say XD. X is any except, guess it should probably be non-empty. It doesn't matter. And then what D is So D is called the metric. It's a function from x times x to R called a metric or distance function. So a metric space is supposed to be a set where you have the notion of the distance between 2 points. So D PQ is what we call the distance from P to Q. What should the properties of that be? Well, the distance from P to Q is greater than or equal to 0. The distance from P to Q is equal to 0 if and only if P is equal to Q. Distance from P to Q is the same thing as the distance from Q to P. So these are all things that we already intuitively feel about distance. Finally, the distance from P to Q is less than or equal to the distance from P to some other point R plus the distance from R to Q. I think we had seen this before. This last bit is called the triangle inequality. I think we had this picture once, so if I have P, Q, and R, well, what we know about distance in the plane, for example, we see that the triangle inequality is true in this picture. Distance from P to Q cannot be greater than the distance from P to R plus the distance from R to Q. Okay, so why are we going through all these definitions? What does this have to do with topology? So I have to give you one more definition before I say something interesting. So here I have BPR. So I'm going to define a set in my metric space. So this is the set of all points Q in X such that the distance from P to Q is less than R. Here R is a positive. So actually this definition should look familiar from when we talked about an open disk in the plane. This is called an open ball in X. So this makes perfect sense in any metric space. So why am I telling you about all these things? Let's call this a theorem. This is nothing too difficult, but it takes a while to write on all the details of this. So I told you these definitions were in increasing order of generality. A normed vector space over R is a metric space if we define the distance in the following way. So maybe let's switch back to V and W. So V and W are vectors in a normative vector space. So a good definition of distance, one that works, that actually gives us a metric space, that satisfies all the properties of a metric space, is to take the norm of the vector V minus W, where, if you're not sure what V minus W means, V minus W means V plus the vector minus W. So a normed vector space becomes a metric space if we make that definition of the metric And a metric space becomes a topological space. So a metric space is a topological space, as we've been studying, if we define, so what do you have to define to have a topological space? But you have to define the topology, which means you have to define the collection of sets that you call open sets. So in fact, we can use an idea that we saw earlier, the idea of the topology generated by a basis. So here you can take the topology to be generated by open balls. So a normed vector space gives us an example of a metric space, and any metric space gives us an example of a topological space. So in particular, a normed vector space is an example of a topological space. So we had seen that example at work already. This is exactly what happened. Well, actually, even R. So R is a vector space over R, and the norm is just the absolute value. So therefore, it's a metric space and also a topology. In fact, if you take the distance, so the distance in the real numbers, distance from x to y is just the absolute value of x minus y. In fact, we had called it earlier the distance from x to y. And in fact, this will if you take T to be the topology generated by open balls, which really so that's the other thing we could say is that what are open balls in this topology? They're open intervals. In fact, bounded open intervals. So that was our first example we had seen a while back. And this works in R2 as well. This is exactly what we saw in R2. So, well, we have to say, so even first of all, what do we mean by adding points in R2? That's worth saying. So how should we add x1, y1, and x2, y2? And we kind of add them in the most naive way possible. x1 plus x2, y1 plus y2. How do you multiply by a real number? How does scalar multiplication work? Well, alpha x, alpha y. And then we just have to say what the norm is. So the norm is exactly what we had mentioned earlier as the distance from 0. The distance from 0 would be something like this: x squared plus y squared. And you see that now the distance from x to y, the distance between 2 points in R2 is exactly the distance that we're familiar with. In fact, the topology is the one that we're familiar with. I guess for fun, let's write it out. Maybe let's not write out the distance formula. The topology. So what are open balls? Well, they're what we called open disks. Okay, so this discussion generalizes what we were discussing earlier. X is any set. Well, here's a good question. Actually, if I give you any set, can you turn it into a metric space? Can you find a metric? Notice you can't just say, oh, make everything 0 or make everything 1. That will violate some of the rules of the metric space. But what you can do is you can very carefully choose when it's 0 or when it's 1. So if you say it's 1 if P is not equal to Q, and it's 0 if P is equal to Q. This is a metric space. So this is a metric on X. Now you can ask, so what is the topology we get? Like? In fact, let me say it this way. What is the open ball centered at P? In fact, let's just put R here. So these are all the points in X that are within a distance of R from P. So in fact, if I say R is less than or equal to 1, what is this set equal to? It's the set that only contains the point P. So what did we learn about if you take a basis consisting of all the points, you take a basis where the basis elements are just one element subsets of X, you get the discrete topology. So we say, so in this case, D generates the discrete topology on X. So all subsets of X are both open and closed. Okay, we were also talking about subspaces. So let's move on and say, so here XD, any metric space, and Y is a subset of X. Well, what I can do is I can take D, it's kind of like restricting it to Y. I can use the metric on X to define a metric on Y, or I just simply use the same formula, just on a subset of X. So we can ask, is this a metric on Y? Is Y, D restricted to Y? Is it a metric space? Yeah, it is. This is a metric space. So now we can ask, what is the topology generated by the metric? And we get exactly what we should. We get the subspace topology. So D restricted to Y generates the subspace topology of Y. The one that's, as we discussed, the one that's induced by X. There's some details to check there. That's what happens. So for example, just to show you what I'm talking about, you could have Y equal circle, which is an X, which is 2. So a circle in R2 is a metric space. How does the metric work? Well, it doesn't work exactly in the way that you might want it to. So actually, the distance from P to Q on the circle is just the distance in R2. So the distance from P to Q is just what we think of as the length of the line segment. So, but the fact of the matter is it is a metric space. Okay, so a circle with this metric, so we're using the same, using the metric in R2, so the norm of P minus Q. Sure, it's a metric space. One thing you might note, let me go to the next page. So the point is, maybe there are other ways to think of this as a metric space. Is there another way to think of the distance from P to Q? If you were actually standing on the circle, and you wanted to know, like if your entire universe was a circle, and you wanted to know the distance from P to Q in your universe, you might not measure it in the way that we're measuring it here. You might actually measure it by walking around the circle. So a note here is that this might not be the way that you were thinking of the distance. So there is perhaps a more, I'll use this word, intrinsic way to measure distance in the circle. So, for instance, from geometry, we know things like this. What's the circumference of a circle? It's 2 pi times the radius. So already some complicated things to make precise. I mean, what is pi exactly? But we have this idea from geometry that the circumference is 2 pi r. So if you take an angle, another idea from geometry, so you could say that, so this is the angle, this is an angle in radians. This is P and this is Q. Oops. So what's maybe a more geometric way of thinking of the distance from P to Q? Well, it's as it's the length of the arc on the circle. So I guess what would that be? Theta times r, right? R is the radius. So what I'm claiming here is that this more geometric way of thinking of it, I think also works. So this d is also a metric on the circle, and in fact, this might be a good. So we can call this a problem for you if you want, just to show or explain somehow, however you want. Show that this d is also a metric on the circle and generates the same topology. So it generates the subspace topology. So that means using R2. Okay, so here's a definition. Rn. So we've seen, we've seen R without the n up there. That's the set of real numbers. We've also seen R with a 2 there. That's R2, the Euclidean plane. So Rn is the set of all ordered, we call them n tuples. Say x1, comma x2, until you get to xn. So each xi is a real number. So this is just naturally generalizing what we did with R2, except now we don't just have a pair of 2 real numbers. We have a list, an ordered list of n real numbers. Okay, so that's simple. But when it becomes more interesting is so it actually we can define addition. That's so if x is this element of Rn and y is this element of Rn, we can define addition simply like this. So the first number is x1 plus y1, the last one is xn plus yn. Can define scalar multiplication. Also in a simple way, like this. Just multiply each number by alpha. And then the norm. Well, once again, the norm is a natural generalization of what we saw in R2. It's the sum of all the squares of the numbers, and then you take the square root. In fact, this, so R3, we're supposed to think of as 3-dimensional space. So that formula for the norm actually is supposed to make sense. It actually will give us the length of this line segment in R3. So if this is P X, I guess. So if this is element X in R3, then you can really work out geometrically that that should be the norm of X, the distance from X to the origin. Okay, so the whole point is that Rn, I mean, there's lots of little details to check, but it fits our definition of a normed vector space. It's a normed vector space, so we've already even have said how that gives us a metric space. And we've said how a metric space gives us a topological space. So the distance is given by the formula we saw. It's the norm of the when you subtract 2 vectors. And the topology is generated by open balls. So in R3, what's an open ball look like in R3? So B, say B, X, R? Well, this is where the word ball is especially descriptive because it really looks like a ball. So what it is, if I have a sphere, it's all of the points that are sphere of radius R is all the points that are strictly inside the sphere of radius R in R3. Okay, so here's something else we can do. So we have Rn. So can we put an infinity there? What should R infinity be? In fact, I'm going to put a 0 here. You might say that R infinity just could be the set of all sequences in R. So sequence just means that, so I start listing real numbers, but the list goes on forever. I put the 0 because if you wanted, you could take all such sequences, but what I'm actually interested in, because I want to get a normed vector space, is such that xn is equal to 0 for all n, let's say, greater than or equal to some n. So that means that my sequence looks like x1, x2, x3. Eventually I get to, it doesn't really matter, say strictly greater than if you want. Eventually I get to some number xn, and after that point it's constantly equal to 0. So R infinity with a 0 there, just to remind ourselves that of this condition here, that xn is equal to 0 for a sufficiently large n. How would you add two such sequences? Well, just in the same way as before, only you have infinitely many things to add. x1 plus y1, x2 plus y2, etc. So that works out just fine. Same thing with scalar multiplication. Just have to multiply infinitely many numbers. Well, it's eventually 0. And now, what you can do now, so how can you define the norm of x? So this is where the x is x is the sequence, x1, x2, etc. Well, this is where that condition that they're eventually 0 is important, because what I want to simply do is this using some notation that you might remember from calculus. The sum from I equals, or n equals, let's say, 1 to infinity of x n squared, and then I take the square root. So we don't have to worry too much about this making sense. I'll write this down again on the next page. So the sum, the square root of the sum, 1 to infinity, x n squared. So, I mean, infinite sums are, you have to be careful how you define them. You study them in calculus. What does it mean to add infinitely many numbers? But there's nothing to really obsess over here. So this is defined since only finitely many xn are non-zero. So really, this is just a fancy way of saying add up the squares of all of the non-zero numbers in the sequence, and then take the square root. Makes perfect sense. There's no weird things to think about. So, this is another example. My R infinity 0 is another example of a normed vector space. Fits all of the requirements of a normed vector space. Okay? So, let me point out something that's different. So, Rn, I won't give the definitions of these things, so just take it as terminology if you want. Rn is what we call an n-dimensional vector space overall. Whereas my R infinity 0 is an infinite dimensional, which is infinite dimensional. Those are some concepts studied in linear algebra. So it means that this is not, so R infinity 0 is not spanned by finitely many vectors. We don't need to think about that too much though. Okay, one thing to note is that our definition of convex makes sense in any vector space. So we want to think back to some of the things we studied in topology. So we have the definition of convex in R2. Actually, I gave you the definition of convex in R3 as well, very early on, just in terms of what a line segment is. Our definition of convex makes perfect sense in any vector space. In fact, so you can write it out. So all we have to do is say, what is a line segment? Well, it's this. So here I have the set of all vectors in my vector space. So T is a scalar in 0, 1. So this is what we mean by the line segment. V2. So in fact, this agrees with our definition of a line segment in R2, if you look back. So I'm only telling you this so that we can say something like, I mean, what we said before about convex implying path connected. This is true in any normed vector space. So convex is defined in terms of what a vector space is. Path connected is defined in terms of topology, but every normed vector space, well, is both a vector space and a topological space. So this statement is true in any normed vector space. And we know that this, so remember that path connected always implies connected as well. So if you want, you can add that in parentheses. Of course we know that this also implies connected. Convex implies path connected, implies connected. This makes sense in any normed vector space. So it makes sense in Rn. So e.g. Rn, and also in R infinity 0. Those are true statements. So, for example, any normed vector space go to the next page. So I mean, there's some immediate consequences of these things. For example, any normed vector space, when you think of it as a topological space, is connected. You can never, ever, ever have a normed vector space that's disconnected. If you know what a subspace is, it's okay, so any vector subspace of a normed vector space. Any vector subspace of a normed vector space is also connected. So what that means is that I have W inside of V. If I have V and W inside my big W, and I have alpha, which is a real number, I know that V plus W is in V, and I also know that alpha is V. Oops, in W, I mean. This. So in fact, both of these are elements of W. So I'm just telling you, if you don't know what a vector subspace is, I'm telling you right now. So, I mean, for example, R3, three-dimensional space. Is it connected? Yes, it's connected. Okay, it's a vector space. It's a normal vector space. It's connected. And you can take any subspace. So what do subspaces look like? They look like planes through the origin. So V could be R3. W could be plane through the zero vector, the origin. It's also connected. We don't even have to worry about that because we know it is a vector space. It is a normed vector space, so it's connected. Okay, so we've been seeing a lot of connectedness lately. Should we push further, or should we stop, guys? Okay, so now's a good time to stop, I guess. Yeah.
Norm vector space is topology, right?
That's right. If you don't have a norm.
I was wondering if you could have a vector space and come up with a topology.
Yeah, they're what are called topological vector spaces. Sure. So you could just have a vector space with a topology. But you get some strange. Yeah, you get some things.